thought it's interesting and important to see another example where you have similar ideas. So in the steady case, you have also important information about the asymptotic geometry. Then you have uniqueness, so you can classify. It's not a complete classification yet, but it's almost there. So unfortunately, we don't know anything about the 4D. There's no general classification in 4D. So I have to drop one dimension and talk about 3D steady solitons. So here we have good information. We know a lot of things. And this owes a lot to a theorem by Brendel, which was, of course, the statement was mentioned in Perelman's papers. So steady solitons, I will assume the manifold is 3D and that Ricci plus the Hessian of F is equal to 0. So that would be my notation. Because of that, the function F is actually not positive in this case, it's negative. So F will be, expect F to be minus distance. So it's not really positive in this case. So the theorem I'm interested in, so I will talk about the following theorem. It's again due to Brendel, and it's a different type of uniqueness. So it says the following: if MGF is 3D kappa non-collapsed steady soliton, then it's rotationally symmetric. And hence it's Bryan soliton. So it's a classification, and the reason I said it's not yet finished, because if it's collapsed, we have no real information. We have some information, but not complete. If it's non-collapsed, which is related to the Ricci flow, it's done. So this is the classification. So why did I say it's about asymptotic geometry and uniqueness? The kappa non-collapsed, I'm not even going to define it. I'm just going to say that this is work by Perelman, and that's all we need to know. That's where the kappa non-collapsing is used. That basically Mg is asymptotically cylindrical, but in a different sense. So not the way I talked about last time. What I mean is it's in the flow sense as an ancient solution. So basically you take Gm of S. So again, I'm going to use S for Ricci flow, not T, because T will be used for the level sets of the function. So you rescale your metric. So I should say S here. So you rescale your metric by a sequence. So Rm is something that goes to to infinity, so it's 1 over R of Pm. So, S of Pm. S is the scalar curvature. Yeah. So this will be S, and that will be capital S. That's because I used S for scalar curvature, not R as commonly used.
Basically, sectional curvature is positive.
Oh yeah, sure. But right, of course. So maybe I should just say non-flat. Sure.
Essentially positive.
Yeah. Oh, the same for shrinkers, right? I eliminated that in the very beginning. I said that we don't care about flat. So this one converges to so this converges when m goes to infinity for such sequence converges to a cylinder. So in this sense, it's asymptotically cylindrical. So cylindrical, of course, if I think in terms of the Bryan-Soliton, that I said is not cylindrical, it's parabolic. But the rescaling brings these two together until it becomes a cylinder, right? So rescaling, the diameter, this is the level set, this is f is minus t, right? Diameter behaves like root t. But when you rescale, so when you take GM, so this is with respect to G, this is with GM, this would be a constant. So when you rescale in this way, because this is really, this is T. This is T. So then you rescale, you just get something bounded. And well, Perelman proved by in his papers that you do get splitting at infinity, and therefore it has to be spherical. The factor has to be spherical. So this is similar to the previous setting, right? Where you know asymptotic geometry, and you want to prove uniqueness, but it doesn't really work like in the previous theorem. Like in the shrinking case, because of the rescaling by this factor. So it's not really, the flow itself doesn't converge towards the cylinder, it's the rescale version, rescale flow that converges. So we are going to follow a different approach. So the kappa non-collapse is not used anymore, so the only thing we need is that you have this convergence to the cylinder, and we start from there. So the idea is the following. Use the Killing vector fields on S2 to construct Killing vector fields on sigma of t. So I want to construct Killing vector fields on sigma of t. 3 of them. So all the symmetries of the sphere of the limit S2. Of course, this is isometric. Diffeomorphic to S2, right? But I want to construct the vector fields so that I prove it's isometric, not just diffeomorphic. So that's the idea. This will imply that sigma of t is round.
So this basically says infinity is rotational symmetric.
Right now we only know it's diffeomorphic, but if we can construct the Killing vector fields, all the symmetries of the S2 in the limit, then we know it's round. That's all. So I'll just do it for one vector field, so to simplify notation. I'm just going to import one vector field from S2 and produce it on the level set. That's the idea. But it's not really working if you do it by using the Cheeger-Gromov convergence theorem. So you don't want to work on that because it's not obvious how to control, right? You can pull back the vector field, but it's not obvious how to control it or how to prove its killing. So what you want to do is exactly what we did in the shrinking case, where you know it's asymptotically conical, but you have a very clear description of the convergence, right? You know how is it asymptotically conical. You know you know what the section is, you know what the diffeomorphism is everything is explicit. So we try to do that here as well. We try to construct that diffeomorphism, so we want to be more specific about this convergence. So first I'm going to take phi sub t into sigma of t. So to simplify notation, I'm not going to work with this f. I'm going to define capital F to be minus F. So this is like distance function. So I don't want to write minus F everywhere. Then sigma of t is just F equals t. So let's do that. And then I will define by d phi sub t over dt is grad F over grad F squared. Exactly as before, this maps level sets into level sets, and it's a diffeomorphism. And exactly as before, we want to define a metric on the level set. You will recognize exactly what we did for the cone, right? We pull back metrics from the sigma of t onto here. So this is on sigma of t naught. Of course, this is diffeomorphic to S2, right? It's a diffeomorphism to S2, but it's not isometric yet. So define this metric on S2. T is not, so the rescaling is that done linearly. So T here is not T from shrinker. T from shrinker is quadratic. T here is linear. So it's a different kind of rescaling. So it's a parabolic, right? Rescale to cylinder. So I will define this metric on a fixed level set. And exactly like for the shrinking case, I will attempt to compute and prove that gamma t converges to a gamma bar on sigma of t naught in C infinity. So that's about maybe 1/4 of the paper. It's not easy. For shrinking Ricci solitons, this is trivial. Once you know curvature decays, this was trivial for shrinkers. For steady, this is a real piece of work. So you have to do. So let's just attempt to compute and see where we get stuck. So this is 1/2 times -1 over t squared from here. So you do get the Lie derivative, but that's exactly Ricci. There is no 1/2 to cancel out with this guy. The shrinking had a 1/2 G that cancel out with here, and you got good decay. So here the problem is you don't have that. I think it's 2 Ricci, right? It's a Lie derivative, so it's 2 Ricci. So it's 1 over t times Ricci minus 1 over 2tg. That's the problem. I need to show this thing converges to 0 very fast. We know it converges to 0 because it converges to a cylinder. But we need to get a good decay information for this one. So we need explicit decay for Ricci minus 1 over 2tg. So we do know this decays to 0, but we need to know explicitly so that we can plug it in here. So that's the difference between, this is what complicates the issue, and this really the proof that Brendel gave for this uses a lot of estimates. So it's a lot of work to get that extra information about the decay rate. So Perelman there says only that it converges, but not decay, convergence rate. So you know it converges to the cylinder, but you want to know how fast. You want to know explicitly how fast it does so. And it's some work there. So I'm going to skip that and eventually get. I just wanted to point out that here you have to work harder than in the shrinking case to get that information about the convergence. Eventually you get that d gamma t over dt in any norm ck is less than some constant over t to 9 over 8. So he can push. So 1 over t you already have. Then you can push to 1 plus 1 over 8. So that's a lot of work. And this, again, you integrate and you're able to prove that gamma t converges to gamma bar, I think I called it.
So is the gamma bar the restriction metric on the original?
On one level set.
That's right, original metric, right?
Yes. So this one. So this is the metric on the level set.
The gamma bar is the original metric is your sound.
This is the limit.
No. Yeah, but
We don't know yet. It's just it's a round metric, so we don't know if it's the original metric. That's what we want to prove. Yes, that's what we want to prove. So it is round metric because once you know this goes to 0, then if it goes to 0 fast enough, it implies it's actually the S2 metric. So gamma bar is round metric. But we want to show that it's actually the same as the original one. Okay, so now we know exactly what how the convergence happens. It's not just Shiger-Gromov theorem, so abstract theorem. It's actually you pull back the metrics, you rescale them, and you take the limit, and that's how you get the round metric on S2. It's exactly like in the shrinker, but the difference is in the shrinker, that's how we proved that kind of theorem. Here we use the theorem and a lot of other estimates to prove this. Okay, so now the idea is, since this is the round metric, there exists U bar 1, U bar 2, U bar 3, which are killing vector fields on S2, so on this, with respect to gamma bar. So again, I'm not going to keep all this, so let's just generically call this U bar to be one of them. Any one of them. To save time, right? Otherwise I have to keep writing 1, 2, 3. So U bar will be a killing vector field with respect to gamma bar. The idea is now to produce a killing vector field with respect to G. If we do that, we're good. So, first of all, we can define U to be the pushover of phi of this U bar. So this will be a vector field on sigma of t. You can do this for any t, right? So you get a global on M. Actually, you get it only outside the compact set because these are not defined for all t. So it's only for as long as the level sets are smooth. But then you extend any way you want to be a vector field. So right now we're not very picky. We just want to construct a vector field with good behavior at infinity. So we can do this for any t. We get a global vector field on M. So now let's see. Since gamma t minus gamma bar. So this is 1 over 8 comes from 9 over 8 from before, right? I did say here you have 1 over 8, 9 over 8. You integrate, then the difference between them is 1 over 8. Then you can compute that the Lie derivative of this is, okay, so we have to compute the Lie derivative of U and here gamma, and here g, right? So we want to see Lie derivative of g with respect to u. U is related, it's the pushover of u bar. So u is given in terms of u bar. But u bar was killing with respect to gamma bar. So the first step is to relate, because of the relation between gamma t and gamma bar, you have the Lie derivative of gamma t with respect to u bar is small. That's because these two are close. Okay, so that's one thing. And then the next thing is to notice that this also implies the same thing about Lie derivative of g with respect to u. So this was obvious because the metrics are close, and this is comes from here. G is the pullback and rescale of, right? So G is pullback and then you rescale. This is the pullback of u is u bar. The pullback of G is gamma t. So this would be clear. Then you have to think what happened to the rescaling. Where is that gone? It's because this is with respect to gamma t. This is with respect to G. So the rescaling is just canceling off. So that's all. So you know that's small. The less obvious fact, which needs proof, is that actually even the Laplace of u is also small. This one, it's something 1/2. I guess from now on I'll just call these numbers epsilon. The number itself is not important, just that there is some epsilon. Right? So I can just call them epsilon to save time. Now let me explain the second one, why the second one is important and why it's not obvious. First of all, u itself grows like root t on sigma of t. That's because of the rescaling. U is, the pullback of u is u bar, but u bar is a fixed vector field on sigma of t naught, so that's bounded. But when you pull back, you rescale by 1/2t, right? So if you go forward, you multiply your vector by root t, because this is length, so it is like root g, right? So that's why this behaves in this way. But then if you do derivative of u, this is a constant. That's because u is vector field, so it has it's contravariant, right? You do covariant derivative, it cancels off. The scaling doesn't matter anymore. If you do two derivatives, actually it's even better, right? This time you have two derivatives, so this will be like ui jk, right? Then the fact that you do two covariant derivatives, one kills off this one, the other will give you root t. That's why this is so precious, because it says more. It's not just root t, it's root t plus epsilon. Where does it come from? It comes from here. If you trace the Lie derivative, gives you Laplacian, right? So since the Lie derivative is small, then the Laplacian f can be proved to be small as well. So now you're kind of in a good shape. You know u grows like this, but note that Laplace f of this thing. So this root t means root f, right? So let's do Laplace f of root f. Well, Laplace f of f, you can check it's 1. The different sets of formulas compared to shrinkers. So this is 1. Laplace f of root f, this is like 1/√f. So this seems a little weird, right? That you have a killing vector field which grows like root f, but its Laplacian actually decays faster than what you would expect. So you can build on that. That's the idea. So now it's the hardcore part of the proof. So it's really So far it's just ideas and strategies, but then then you have the estimates. So let's see how that goes. There are several steps which I'm not going to prove. I'm just maybe give you some intuition or idea of proof. Step 1, solve Poisson equation for vector fields. So given Q, a vector field, with decay exactly like you see over there, there exists a vector field V with decay exactly like I said here. If you have root f, you would expect the Laplacian to be 1 over root f. If you have faster than that, you would expect this to grow slower, right? So the growth rate would be f to 1/2 plus minus epsilon. So slower than root, right? So maybe since I use t, let's put 1/2 minus epsilon. So you can construct a vector field which grows on the level sets. So this is on sigma of t. The vector field is defined everywhere, but on sigma of t, it grows like this. Faster than root, then over there it's also better than root. Such that Laplace f of v equals q. So you can solve the Poisson equation for vector fields. And the idea is very simple. You solve on compact domains with zero boundary, then take a limit. You need to control the C0 norm of the vector field. That's the hard part. So how do I know? It's zero on the boundary, it satisfies the elliptic equation. How do I know it's bounded on everywhere? This is a vector field, you don't have gradient estimates, things like that. So that's the hard part. And it's not true in general, so he's using the cylindrical asymptotics of the manifold. So it's a very specialized proof for this setting. But you can solve it. So I have in mind to solve exactly for that. So apply step 1 to Q, which is Laplace f of u, which does decay exactly as required. So Laplace of u minus v is 0. Of course, if u and v are equal, that would say nothing. But u and v are not equal because, so w is u minus v, w behaves like root t. Because that's how u behaves. And v is slower. So that's where you use the fact that basically you're perturbing u, right? So u itself has good equation, and you're perturbing a little bit, and you get, let's say, harmonic vector field, right? So that's our second step. You can construct a vector field which is f harmonic. But then you have an important fact which can be checked directly by Ricci identities. If you have a harmonic vector field, then h, which is the Lie derivative of the vector of g with respect to that vector field, satisfies the Lifnerowitz Laplacian of this h equals 0. So this is just the usual f Laplacian. So the usual f Laplacian of h. H is a 2 tensor. So it's the usual f Laplacian minus 2 Riemann h. Right? So as a tensor, it's obvious, right? It's Rij. This means Rijk L Hk Hjl. So we've seen this before, right, in equations for Ricci curvature. This is it's just you just compute by Ricci identities. So to commute derivatives, you compute by Ricci identities, and you check that this is true. So the strategy then, try to prove H is identically 0. If you have this equation. That, if you prove, you're done, because that gives you a killing vector field. So then you're finished. It doesn't really work, so I will show that this works if H decays fast enough. So this is a Liouville theorem for two tensors, and if H decays fast enough, meaning something like t to 1 plus epsilon, and then you do get it. You do get this true. Okay? So it is true if we know that, or if we can prove that H decays fast enough, then that's true. So this is a result by Anderson and Chow, and then Chow. So you will recognize this in a moment. Or maybe this is the kind of quantity that Hamilton considered, right? And in the shrinking, the first lecture, I said that we do Ricci square over S squared, or Ricci square over S to the A, where A is between 0 and 2. So actually, if you do Ricci square over S squared, Hamilton proved that this is always non-negative. In his 3D paper, he calls this P over S cubed, and P is just a sum of squares. So that's exactly the result. This is a 3D result. And Anderson and Chow observed that you don't necessarily need to put Ricci here. You can compute exactly the same as Hamilton, except that now all you need is H to verify this equation. Why? Because this is exactly the equation that Ricci verifies. So just follow the argument of Hamilton, and you don't necessarily need to have Ricci. You can have any tensor that satisfies the same equation as Ricci. So note here that Ricci is such a tensor. H may not be equal to Ricci, may be something else, but Ricci is one such tensor. So let's see what we know. We know that this function is subharmonic. So by maximum principle, H squared over S squared is bounded by H squared over S squared at infinity. So this would be on the boundary of a ball. So it achieves the maximum at on the boundary, so at infinity. But this goes to 0 because I assumed H is very fast. So I assumed H is faster than scalar. Scalar, right? So scalar is like grows like t, 1 over t, and H is 1 over. It's better than scalar. Therefore, this beats S. Then it goes to 0. So that would prove H must be 0 if we know 1 over t plus epsilon. But we don't know that. So actually, for us, that's unfortunate. But for us, we only know, I think, 1 over t to 1/2 plus epsilon, or something like that. Actually, only, when you compute, it's only t to the epsilon. I guess when you check all the details, it's just t to the epsilon, because that's 1 over t, root t plus epsilon, but then you take Laplace f and so on. So in the end, it's not good enough. So maybe one way to solve the issue would be to try to prove better decay. But that would mean go back to all the estimates that Brendel proved and maybe show that once you have those estimates, you have even better ones. He doesn't do that, so he doesn't iterate the estimates to get better. I'm not sure if it's possible. What he does is that he shows this is good enough though. So he proves that in this case, maybe h is not 0, but h is the only thing that's left. Ricci. Ricci is also a candidate, right? Because I said Ricci also verifies the same equation. Of course, has the same decay, so it is at most t to the epsilon. So he proves that the only two ones that we know, Ricci and h, are the only one. So a uniqueness of the kernel, right? So there's only one tensor with such decay. So that's what he proves. Then let's go back. Is this good enough? It's not 0. We wanted the killing vector field. So is that good enough? H was Lie derivative of G. But Ricci is also Lie derivative, right? Of grad f. So W minus grad f is killing vector field. Of course, you're also worried here that maybe it's just 0, right? It trivially satisfies the equation. It's not, because this doesn't decay and this decays. So it's a perturbation of grad f. It's not really, they're not equal. That's all. You do this for each of them, and then you get the solution. Then you get the proof. So, roughly speaking, you have one step where you get a precise convergence information about, right? So you know this gamma t, which is your metric, gamma t converges to the round metric, just like we did for shrinkers today. But here it's more work. Then you construct the vector fields, which only approximate, they're only close to being killing, not killing. But actually, he doesn't use that much. So this is the starting point, that this is also small. Then you solve the Poisson equation and you get a perturbation of that vector field, which is really 0. So you get this. Then that, again, by Ricci, by a direct computation, it shows that the Lie derivative of G satisfies a PD, an elliptic PD. Then you prove a Liouville theorem for two tensors. You prove that such H must be 0, or if you want, it must be Ricci, and that finishes the proof. In the process, you have to make sure that if you start with 3 vector fields which are independent, right, which and the brackets generate brackets of 2 generate the third, and so on, that is preserved when you do all these operations. So you have to be careful to produce really 3 killing vector fields, not to miss anything. Okay? Yes?
The Anderson Chow principle, why do they consider f plus 2 log n?
This goes back to Hamilton, where he takes Laplace f. When you take Laplace f of a quotient, you get some terms, mixed terms, right? You take Laplace f of u over v, it's Laplace f of u over v minus Laplace f of v over u, plus Laplace f of 1 over v times u plus 2 grad u times grad 1 over v, right?
It's just a gradient term.
So you have these mixed terms which you have to control somehow. And he's combining them, he's changing the weight so that you can control these terms. So the short story is, if you try to compute the Laplace of the product of two functions and use maximum principle, that would never work. If you try to do the quotient of two functions, that will always work. But you have to change the operator. It's not Laplace f, it's Laplace f plus whatever. If I would change here any function, I would put here u squared, then here I put u. Okay, so that's all. It's a computation. So this goes back to Hamilton's 3D paper. Yes? So finally, I have about 10 more minutes, right? We started at 20.
That's okay.
That's okay. I didn't know.
And of course, we started at 20 because I was late in the first one. So I.
Yeah, you do a long time because like they can
Yeah. Well, maybe I should finish soon. I just want to say that there is some more development. So more recently, Deng and Zhu, they proved that actually you don't need non-collapsiveness. So they proved the following theorem. The previous theorem is true if kappa non-collapsiveness is replaced by a two-side bound of the scalar curvature. So you don't need non-collapsing to take that limit. Actually, you can prove non-collapsing if you know scalar curvature has good control. This is useful because if we want to classify all steady Ricci solidons, then we kind of need to go beyond non-collapsing. And that's a very technical assumption. So how do we achieve that? We just replace it with a more geometric assumption. Why the proof is to prove that if this is true, then it's non-collapsed. But not G itself. We can't prove G itself is non-collapsed. We prove that the rescaled one, the one I mentioned in the beginning, which is has injectivity radius positive. Right? So non-collapsing is used to. So forget all the non-collapsing and everything. You just need to prove injectivity radius for the limit, for the rescaled one. So you have the solidon, then you rescale. This, you have a certain diameter, you rescale it by this. You want to prove that the injectivity here is positive, right? That's all. So how do we prove that? Well, you have that curvature information and use exactly like we used in 4D, that the level set is 3D, so curvature has more information. Use that sigma of t is a 2D compact manifold, right? So that means two things. On one hand, it means that the curvature, the Gauss curvature of sigma, is determined by scalar curvature, and then you have the normal directions. So on one hand, you have this information. This is Ricci curvature, but this is like constant over r squared, right? Because a scalar is r. It's 3D, so scalar determines everything. And that's r squared. You can prove that this is also r squared. But that's very easy from the formulas. And this is 1 over r. So then it means the curvature of sigma is bounded by constant over r. Or if you do the rescaling, the rescaled surface has strictly positive curvature, bounded below. So that's the first observation, that really you have you have a lower bound, and actually, and of course you also have the upper bound, right? That's also true. So in fact, this implies also diameter estimate. I should say t here, right? Because I used t for the distance. This is before rescaling, right? After rescaling, you just get c and c minus 1. Diameter will be like root t. And that follows from Meyer's theorem, because it's positive curvature. Gauss-Bonnet implies that the area of sigma of t must be constant t, right? Because the curvature decays in that way, and it's a sphere, diffeomorphic to a sphere, so it must be constant t. So you get the information about the asymptotic geometry without using any limits, without using Perelman, just by taking this approach. So then this is before rescaling, right? So diameter root t, area is t. After rescaling by t, you get area is constant and diameter is also constant. I mean, bounded from below and above by constants. And then that implies the injectivity radius, implies the volume lower bound. So you can use that to get the volume lower bound. So that's all. So you don't need non-collapsing. All you need is 2 bounds. So now where things are going is that we hope that we can classify 3D without making any assumptions. So and that will end. So by classification, I mean complete, without making any assumption. So we know that if scalar behaves like constant over R, it's done, right? This is by Deng and Su and using Brendel's result. Now, what we can prove is that if scalar curvature is faster than that, so if it's faster, if it's exactly linear everywhere, then you're done. If it's faster than that, then the manifold must be a quotient, must be cigar across a circle.
All directions.
Sigma here is the cigar, so I should say cigar across the circle. But I assume in all directions, everywhere it's linear, faster than linear. So this is faster than linear. Okay, so the proof actually owes a lot to some previous work by Deruel, who showed that if if the scalar curvature is in L1, if it's integrable on the manifold, then you have this. So we did two things. On one hand, we provide a different proof, shorter proof of this result by Deruel. But I don't want to insist on that. If you're interested, I can show. And the other hand is exactly like in the conical case. We show that this implies, but this is a simpler proof, implies scalar curvature is exponentially fast. So if it's exponentially fast, it's integrable, and you can use that result. So now, whatever in between, it sounds exactly like the shrinking case. If scalar goes to 0, you know a certain regime. If scalar is bounded below, you have a different regime. What's in between, we don't know. Here it's the same way. Scalar goes linearly to 0, we are done. Scalar is faster than linear, we are done. But maybe there will be directions where it's faster than linear and other directions where it's just linear. Which Hamilton conjectures there should exist examples like that. And in the 4D there are. Poisson constructed an example like that in 4D. Hamilton conjectures there will be even in 3D. Okay, so I'll end with this. And again, if you want to talk more about this, I'm available. Thank you.